Hello, everyone. Okay, so today we're talking about the assignment 2 in physics. So this is for year 11. Okay. Just a second. And let me share my screen. Okay. Okay, lovely. So yes, today we have a webinar on units, measurements, and uncertainties. I hope you'll enjoy it. Usually it's quite a boring topic. Like this topic is considered quite boring because it's like, it's where's the fun in it? It's just measuring uncertainties. But I don't know. It's an incredibly important topic as well. It's like um I I think I was talking to a lab technician, and they said, Why is it so important to you that you get the uncertainties correct?" And he said, "Look, it's very simple. If you take a glass prism, so let's look at a glass prism. So glass prism, and yeah, like this, you know." Um, it's an optical instrument, an important one. And if you order a glass prism and you say, I want this angle to be 90 degrees, and you say, I want one prism 90 degrees, and they say, yeah, that will cost you £1, 90 degrees, or 522, including delivery probably. But anyways, however, if you say, that's what the lab technician told me, but if you do 90.000 degrees, this will cost you £2,000. Okay, maybe more. I mean, I can be wrong with the numbers, but the point is, when you say 90 degrees, what do you mean? Do you mean exactly 90? Well, that's impossible. You can't have a 90-degree angle in real life. It could be as close, it could be close to 90. However, the question is how close? And if you need something really, really, really close, it will cost you a lot of money. Okay. So yeah. Oh, sorry. So 4 days is correct. Okay, so we have webinars, the new assignments. The new assignments are out. This is year 12 assignment. So if you go to our website, we have webinars. If you click on the webinars and you click year 11, you will see the list of webinars scheduled for this year. If you go to assignments, you can download. Oh, apologies. They were supposed to be here, but something went wrong. I will make sure that these are posted and they are available. Sorry for that. Has anyone managed to download assignment 2 for year 11? That was the plan, yes. Apologies, I'm not the person who does the emailing of assignments. Okay, so has anyone managed to get? So it looks like no one has seen the assignment. That is a pity because I didn't. I'm so sorry about this because I did send them off last week and. Well, okay. We'll start talking about the assignment. Let me. Okay, easy solution. I'll do this. So you all have the link to the webinar, the Miro board, and what I will do is I will post the assignment here. So this is the assignment. You can have a look at it. There's a link. The deadline is the 17th of November, so you still have a month to do it. So yeah, we won't give an extension. Apologies, but especially you will only know if you're in or not next week. So yeah. So in this assignment, we talk about units, measurements, and errors. So we start with units. We then move on to conversions of units, and we use prefixes. All right, so then we talk about types of error, and then propagation of errors, and yeah, so things like that. Good. So let's start. Units, measurement, and uncertainty. So as I mentioned, it's really important to know the precision, right, in this particular case. The difference between 90 degrees and 90.000 degrees is the uncertainty. Because when you say 90 degrees means 90 plus minus 0.5 degrees. Basically anything that rounds to 90 degrees. Okay, so the uncertainty in this case, uncertainty is 0.5 degrees. Which is 0.5 divided by 90. If you calculate 0.5 divided by 90, that's roughly 0.5%. 0.5% uncertainty. or 0.6 technically. Yeah. When you say 90.000, that means it's like limits of accuracy. You know this topic from GCSE maths. 90.000 means 90.000 plus. Okay, apologies. 90 plus or minus 0.0005 degrees. So the uncertainty is 0.0005 degrees. And if you divide that by 0.005 divided by 90, that is 0.0005 divided by 90 is 0.0005 6% uncertainty. Do you understand the difference? Do you understand the difference? And do you understand how I calculated the uncertainty? On a scale of 0 to 10, please. This is what is known as percentage uncertainty. Percentage uncertainty. So you basically calculate the uncertainty as a percentage of the actual value. So this is the percentage uncertainty, whereas this is referred to as absolute uncertainty. Absolute uncertainty. Absolute uncertainty. And we will be using the following symbols. So for 90 degrees plus or minus 0.5 degrees, the uncertainty, so this is, let's say this is the angle theta. Uncertainty in the angle theta, absolute uncertainty, is 0.5 degrees. The relative uncertainty is delta. Delta theta is the relative uncertainty, is delta theta divided by theta, which is 0.6%. And here, if you say theta is 90, 0.000 plus or minus 0.0005, we'll be using delta theta is 0.0005 degrees, and delta theta is delta theta divided by theta is 0.0006%. Okay, so that's the way we do this. Okay, but we'll talk about uncertainties in a bit. We'll talk about uncertainties towards the end of this session. Let's start talking about units. We have something that we call base units of the SI system. SI system. Système international d'unités. It's French. The French invented the metric system, pretty much. Okay, so SI system, we have base units. And there are seven base units. It is the kilogram, the meter, the second, the ampere, the mole, Kelvin as a unit for temperature, and candela. You will not be using candela in A-level physics. So if you go to university, and even then, maybe not. Okay, so I, in all my 7 years at university, I never had to use candela. However, if you the other six are very common. So you know kilogram, of course, meter, second, ampere. The thing is that every other unit can be expressed in terms of base units. So let's have a look. For example, express in base units, the Newton. Newton is a unit of force. Okay, so Newton. To work out what a Newton is in base units, we can say, okay, so what is force? Can somebody give me an equation for force? Any equation for force. There are many of them. Yeah, the easiest one is F equals ma. Okay, so F equals ma. Mass, so force. Well, force is measured in kilograms. So the Newton, sorry, ma. Force is measured in newtons, which is kilogram. And acceleration is measured in meters per second squared. So it's kilogram meter per second squared. Or you can write kilogram meter second to the power -2. So this is a Newton expressed in base units. So as I remind you, there's 7 base units, and that's how you express the kilogram. Do you understand this question? Do you understand how to do this? On a scale of 0 to 10, please. Okay, good. All right, so we can move on. Joule. Can somebody give me an equation? Well, joule is energy. Joule. So can somebody give me an equation for energy? Any equation for energy, for that matter. Power multiplied by time. That's a good one, but we don't really know what power is measured in. Well, it's measured in watts, but what is a watt? What is joule per second? So we kind of come back to joule. Selena, a good idea, but Sam, yeah, mc squared. Yeah, could you do mc squared? Or you could do force times distance, fs, of course. So it's Newton multiplied by distance, which is meter. But we already know the Newton. Newton is kilogram meter second -2, and meter multiplied by meter. So meter becomes meter squared. So kilogram meter squared second -2. And our moderator Konstantin has told me that you can use E equals mc squared. Yeah, of course, E equals mc squared. Meter, m is mass. So the unit for energy is mass, which is in kilograms, multiplied by the speed of light. The speed of light is measured in meters per second, and it's squared. So it becomes kilogram meter squared per second squared, which is the same as kilogram meter squared second to the power -2. So you get the same unit, whichever formula you use, which is unsurprising. Energy density. So whatever energy density is, energy density. You don't really need energy density until you go into A level. Energy density is energy divided by volume. It's energy per unit volume. So for example, if you stretch a rubber band, how much energy you use to stretch it divided by the volume of the rubber band is the energy density. So energy density is E per volume. That means it is joule per meter cubed. So it is joule meter to the power minus 3. And joule, we already know that the joule is kilogram meter squared second minus 2 multiplied by meter to the power minus 3, which makes it kilogram meter to the power minus 1 second to the power minus 2. Yes, Sam, thank you. Right. Intensity. That's intensity of radiation, because intensity. Is there another meaning for the word intensity in physics? Can't think of it, but intensity. Intensity is the power intensity. It's power divided by area. But power is energy divided by time divided by area. Okay, so that would be energy divided by time. So it's energy, which is kilogram meter squared second minus 2, divided by second, divided by area, which is meter squared. So this is kilogram meter squared second minus 2 second minus 1, and then meter minus 2 because we're dividing by meter. So now combining the like terms, kilogram combining the like units, so that becomes, ooh, meter cancels out. Kilogram second minus 3. Have I made a mistake somewhere? That is bizarre. Kilogram meter squared second minus 2. So that's the joule divided by second. So it becomes second minus 3 divided by meter squared. Oh wow! I never thought of that. I never thought that intensity of radiation, like solar radiation, for example, yeah, this is actually watts per square meter. That's watts per meter squared. And it's measured in kilogram per second cubed, which is, I don't know, it sounds bizarre. I think I haven't made a mistake. Anyways, let's move on. In the following questions, you need to figure out the unit that we would use to measure the gradient of the graph. Of course, the gradient of this graph, the first line, is 0. But what if it wasn't 0? Like if it was like that? I'm not asking for the value of the gradient. I'm just asking for what unit would you measure it in. So if you were to find the gradient is the change of y divided by change of x. What would the unit be? Let's have a look. So it's acceleration. Acceleration, this is meters per second squared. And this is seconds. So you would do meters second to the power minus 2 divided by second. So that would be meters second minus 3. So the gradient would be measured in meters per cubic second. B, find the area under the graph and give the units. Okay, so find the area under the graph. If you want to find the area under the graph, you're multiplying 10 area is 10 meters second minus 2, and you multiply it by 1 second, which makes it 10 times 1, which is 10. Meters second minus 2 second, so that's meter per second. So that's velocity. And indeed, the area under the acceleration time graph area is the change in velocity. Is the change in velocity. Sam, yes, you're correct. It just means unit. The unit of is that. The unit of energy is that. Um, okay, so here, force divided by second. So that would be force over sec. If the gradient would be force over second, force over time. So that would be Newton divided by second, which is kilogram meter second minus 2 per second. Okay, which is kilogram meter second minus 3. And B, what's the area? Well, to find the area, you split it into 2. You could split it like this, for example. So it's 150 newtons times 2 seconds plus, that's 50 newtons times 0.5 seconds. That would make it 300 plus 25, 325 Newton seconds. Okay, 325 Newton seconds, and that is the area. A Newton second. What is a Newton second? Well, Newton second is the unit for impulse. Impulse doesn't have a special unit, it's just Newton seconds. Okay, here, current and time. So the gradient is current divided by time. So A is current divided by time. So that would be ampere per second. That's easy because ampere is a base unit. Remember, it's one of the base units. Fantastic. And B, if you want the area is 1/2 times 12 amps multiplied by 25 seconds. Oh no, sorry. It's not. If you want the area, it's 6 here, so it's 7. So you kind of have this triangle. So not 12, it's 1/2 times 5 amps plus, and then you have this big rectangle here which goes from 0 to 7. So it's 7 amps multiplied by 25 seconds. So that would be 5 times 25, 62.5 amp seconds plus 7 times 25, 175 amp seconds, which is okay, sorry. Very, very long day. I don't want to embarrass myself by 237 by getting it wrong. Amp second. It turns out that an amp second is actually a coulomb. Because if you have a current running for some time, 237.5 coulombs. Because a coulomb is ampere multiplied by second. So coulomb is not a base unit, but an ampere at a second is. Okay, so here, if you want it's Newton divided by meter, so it's kilogram meter second squared by meter, which makes it kilogram second minus 2. Right, B is the area. Well, we can't really calculate the area. I don't want to do it here, but If you want to calculate the area, you could find, let's say, a point here, and you can approximate like this, and maybe like this. Okay, maybe that's too much, but the idea is you take a straight line. Please don't snap. Okay. So if you were to find the area, this is what I would do. I would find a reasonable point. Actually, that's not too bad. So rather than finding the area under the curved line, I would find the area of these two trapezia, or trapeziums, which is much, much easier. And you can see that the area of this trapezium is approximately the same as the area under this curved line. And if you want the area under this curved line, it's approximately the same as the area of this trapezium. You can adjust slightly, like this point, you can adjust it to make it more closer. So area, the unit for area, would be Newton meter, which is apparently that is joule, because Newton times meter is joule. And this one, so now this is velocity per time, but this is in microseconds. So that would be meter per second divided by microsecond. What do we do with the microsecond? Well, we can substitute. It's 10 to the minus 6. A micro is literally 10 to the minus 6. The short way of writing 10 to the minus 6, and then meter second minus 1. So what you do is you say, well, you take this to the top, it's 10 to the 6 meter second minus 2. So it's an acceleration. It's acceleration. And it's in million meters per second squared. You could say it's megameters, which is equivalent to megameters second minus 2. Why not? Very rarely used. I mean, don't really see people using megameters. It sounds better than it looks. Okay, so it's million. So it's in million. The gradient, it will be measured in million meters per second squared. All right. B. The area would be velocity times time. So that would be, okay, so we can use this triangle here, and then we can use this rectangle. Okay, so the triangle is 1/2 multiplied by 0.4 microseconds multiplied by 4 meters per second, plus the area of the rectangle, which is 2 multiplied by 0.4 microseconds multiplied by 2 meters per second, which is 0.4, that's 1.6 times 0.8 plus for 1.6 microsecond meters per second, which is 2.4 microseconds multiplied by meter per second. This is where you can really do some clever stuff. Second and second cancel. Second becomes like this. So it becomes micro, so 2.4. Micro doesn't cancel, but the second does. The micro stays micro. It becomes micrometers per second. Micrometers per second, which is quite, this is quite significant. So look what I did. So we have microseconds multiplied by meters divided, let's say divided by second. You can cancel the second, the micro stays, and it becomes micrometers. This is a very nice thing you can do with units. Because prefixes have a meaning. And let's just list the common prefixes. So milli, that's M, and this means 10 to the minus 3. Micro, mu, which is 10 to the minus 6. Nano, which is N, which is 10 to the minus 9. Pico, which is P, which is 10 to the minus 12. There's also 10 to the minus 15 and 10 to the minus 18, but we rarely use them. Then kilo, K, which is 10 to the 3. Mega, which is M, 10 to the 6. Giga, which is G, 10 to the 9. Tera, you can use tera, which is 10 to the 12. Now, there are also some intermediates like deci. D stands for 10 to the 1. Centi. Oh, sorry. Deci is 10 to the minus 1. Centi is 10 to the minus 2. So, for example, into centiliters. If you take a bottle of water from, especially from a country where the metric system was invented, they will measure things in centiliters. Yeah, so 50 centiliters. So that's 50 multiplied by C. C is 10 to the minus 2. So 10 to the minus 2 liters. So that is 50 multiplied by 0.01 liters, which is 0.5 liters. Okay, they're quite interesting. Type 1 if you knew this, and type 0 if you didn't. Everybody uses it. Okay, that's. Everybody knows this. Okay. Okay, moving on. Express the speed of sounds in miles per hour. Oh, that's fairly straightforward. And you can, there are different ways you can do this. So first, I'll do the first one, A, B, and C. I'll do A, I call it the straightforward way. So miles per hour. So let's say 1 mile, the speed of sound, sorry. Speed of sound, let's say it's 330 meters per second. 330 meters per second. We need miles per hour. Well, we know that 1 mile is 1,600 meters, or 1,608 technically. So this would be 330 divided by 1,600 miles. That we've replaced meters by miles. And seconds, we need seconds in hours, so multiplied by hours. So one. So you can say you can put one here. Sorry, just confused myself. Yeah, so 1 second, which is, if you to convert seconds into hours. Okay, let's not do this. Let's do slightly differently. 330 divided by 1,600 miles, and here you have 3,600, because there are 3,600 seconds in an hour. Hours. So you can do this like this. So 330 divided by 1,600 multiplied by 3,600, and that gives you 330 times 3,600 divided by 1,600, which is 742.5 miles per hour. This is the straightforward way. When I do unit conversions, I usually do it this way. But there is another way which you can use, using conversion factors, using conversion factors. What is it? How does it work? So the speed of sound in feet per second. So 1 meter divided by 1 meter is the same thing, right? Is just 1. So let's say you have 3 feet is equal to 3 feet multiplied by 1 meter by 1 meter. It doesn't make any sense to do this, but you're allowed to do this, right? Because 1 meter divided by 1 meter is just 1. You're allowed to multiply by 1. But we know that 1 meter is 1 meter in feet is 3.28 feet. 3.28 feet. So we can replace this by 3.28 feet. So we have sorry, we don't need that. We need, we can replace this by feet. So it becomes 3 feet multiplied by 1 meter divided by 3.28 feet. Now feet cancel, and you have 3 divided by 3.28 meters, which is 3.28, which is 0.914 meters. So I know this about meters and feet. So what I'm doing is I'm saying 1 meter divided by 1 meter is just 1, which is the same as 1 meter divided by 3.28 feet, which is the same as 3.28 feet divided by 1 meter. So these 3 fractions are equivalent. So you can multiply your value by one of these fractions, and that gives you the new value. You just need to make sure that the units that you don't want cancel. So the same way you can measure like 4.6 meters is 4.6 meters multiplied by, so I need 1 meter here, 3.28 foot here. Meters cancel, and I get 4.6 multiplied by 3.28, which is 15.1 foot. Okay, so I really hope that makes sense. So let's speed of sound. So we're talking about speed of sound, 330 meters per second. Meters per second. And all I need to do is 330 meters divided by second multiplied by 1 meter, 3.28 foot. Meters cancel, and I got 330 times 3.28, which is 1080 feet per second. Okay, so I hope that makes sense. And C, let's practice using the conversion factors again. So 330 meters per second. I want it in parsecs per billion years. Okay, so I need to use several conversion factors. So parsec. What is a parsec? Parsec is 3.26 light years. Parsec in light years. 3.26, yes. Right. So 330 meters divided by second times 3.26 parsecs divided by 1 light year. What is 1 light year? Well, 1 light year is the distance light travels in 1 year. So it's 330 meters divided by seconds times 3.26 parsecs light years. So 300,000 meters, 300,000, 300 million meters per second and multiplied by 1 year. Okay, because light year, 1 light year is speed multiplied by time, which is 300 million meters per second multiplied by 1 year. That's what I did. And seconds conveniently cancel out. Meters conveniently cancel out. And this is 300 million. So that is 330 times 3.26 parsecs divided by 0.3 billion years, which is 330 times 3.26 divided by 0.3, which is 3,586 parsecs per billion years, which sounds like a lot. But when you when you consider these distances to different stars in our galaxy, you will see that this is just 1,000 light years. That's approximately the distance to Betelgeuse. Distance to in parsec. 131 parsecs. Oh, actually, it's okay. More. Uh, I went the wrong way, but anyways, 131 parsec. It's just one of the stars in our galaxy. So if you travel with the speed of light for 1 billion years, you'd only reach stars in our galaxy. This is how huge. Yes, this will be on YouTube. This is how huge space is. Like even if you travel at the speed of sound, which is 330 meters a second, in 1 billion years, which is 1/4 of the age of the planet Earth, you would travel only 3,500 parsecs. All right. Now, this one is a joke. Question 4. A parsec. Ooh, that's a good question. I don't know if I I'm really tempted to explain the parsec. I'll try to be very brief. What is a parsec? What is a parsec? Is a parsec. Look, imagine, well, take your finger, put it in front of you, and look at it from one eye, close one eye and then close the other. Just keep changing your eyes. When you look at your finger from with your left eye and then you switch to your right eye, it looks like the finger has moved. Obviously, the finger doesn't move, but it's moved. It looks like it's moving. Do you see that? Yeah. So you close one eye, you close the other, and it seems like the finger has shifted. The same thing happens with stars. When you look at stars from a different angle, the position of the stars shifts, just like your finger does. So let's say you have a star, and there, which is a nearby star, and there are background stars. So this is your background. Selena, yeah, can you do that, please? All right. You have a background of stars, and you have the planet Earth. So this is the sun, and this is the Earth. Earth. The Earth goes around the sun. So we have been told. And there's a reason. There are reasons to believe that. The Earth goes around the sun. However, in January, you are here. But in June, you're on the opposite side of the sun. So you've shifted quite a significant distance from your position in January. And you look at the star through a telescope, and it looks like it's just in front of this star A. This is the apparent position of your star. Defined as the distance which one astronomical unit subtends at an angle of 1 arcsecond. So it's a parallax angle. Yes. Yes, that's exactly what it is. Thank you. Apparent position of your star. But 6 months later, in June, it will look like the star has shifted to a new position, B, which is a new position. Just like a finger. Like my finger is right in front of the camera, and now it's 2 centimeters to the right of the camera. Right, so if you close your eyes. So this is your left eye, just as equivalent to your left eye. And this is your right eye. The stars move around. And if the angle of movement, angle, theta, if theta is 1 arc second. What is an arc second? Well, degrees, we have degrees. One degree is 60 minutes. 60 minutes. Degrees, the circle is 360 degrees, but each degree can be divided into 60 minutes. And every minute can be divided into 60 seconds. So 1 minute is 60 seconds. So 1 degree is 60 minutes, which is 3,600 seconds. So it's an angle of 1 second, which is 1/3,600th of a degree. It's a very, very small angle. So if the star is 1 parsec away, this angle is 1 arc second. If theta is 1 second, then the distance, the star is 1 parsec away. Does that make sense, Sam? Does it make sense to anyone else? I hope that was useful. Oh, I hope that was enjoyable. I don't know how useful it is at this stage, but yeah. This one is like it's a joke. A colleague of mine found a book of unusual measurements, and there were bizarre things like express the acceleration of free fall in milliparsecs per fortnight squared, which is absolutely useless, but it's a fun exercise. So let's go quickly through this. Acceleration of free fall is 9.81 meters per second squared. Meters can be expressed in parsec. I can just look up parsec. 1 parsec, parsec in meters, which is 3.086 times 10 to the 16, which is 9.81 times 1 parsec divided by 3.086 meters. Okay, 1 parsec divided by times to the 10 to the 16 multiplied by second squared. Fortnight. So fortnight is I'm not sure if I spelled it correct. Anyways, fortnight is 2 weeks. So it's 14 days times 24 hours times 3,600 seconds. And it's squared. So it's 1 second squared multiplied by 1 fortnight squared. And here you need to put 14 times 24 times 3,600 seconds squared. And now you can do some calculations. So it's 9.81 multiplied by 14 times 24 times 3,600 squared divided by 3.086 times 10 to the 16. So it's 0.0046 parsecs per 0.465 parsecs per fortnight squared, which when we want milliparsecs, so it's 0.465 milliparsecs per fortnight. I don't think there's a symbol for fortnight squared. So yeah, you'll never have to use it. But hopefully you'll never have to use it. Unless the world goes crazy and decides to measure time in fortnights rather than seconds. By the way, interesting story about the kilogram, because obviously the metric system is so much more useful. But everybody in the world used pounds and ounces, and it's like when you go to the grocery store, a pound of strawberries, that's something you can hold. Like the French introduced the gram, right? The gram, and people said, well, what's a gram? Well, it's this much. But how can you explain? How can you explain what a gram is to a normal person, right? Why would a person use grams, which is something you can't really easily understand? What is a gram? It's about this much. That's nothing. That doesn't tell you anything. Now, a kilogram is more sufficient. That's why the only base unit that has a prefix is the kilogram, because there was no chance that everybody would start using the kilogram if it start using the gram, sorry, which was initially proposed as the base unit. They wanted to make the gram the base unit, but gram is too small to use in everyday life. So they've decided to, okay, we'll do 1,000 grams, which is a kilogram. Yeah. Okay. Now we move on to errors and types of error. So look at these four targets, and then you can see that the first image is when you are accurate and precise. And the second one is accurate but not precise, precise but not accurate, not accurate, not precise. Yeah, so this is an example of random error. So random error, that means whenever you take measurements, and in physics you always do measurements, they are prone to some random error. If you measure your height 10 times, you are unlikely to get 10 identical results. So this is just random error. Random error. Okay. This is also random error, but there's more. This is more random error. I don't want to write more random error because it's not really scientific, and I don't want to introduce any terms that are unnecessary in this case. This is known as a systematic error. Systematic error. What does it mean? Because you always get it wrong by the same amount. So imagine you were measuring your mass, and you forgot that you had a bag with 5 physics books in it. Your every measurement would be wrong by that much, right? If you have 5 kilograms in your bag, your every measurement would be wrong by 5 kilograms. Okay, so this is called a systematic error. So it is repeatable. Systematic error is repeatable, and it can be removed. Can be removed. Right. So for example, if you measure, you can subtract the mass of the books and that gives you the systematic error. The random error is not repeatable, and cannot be removed. It can be removed by algebraic manipulation. Well, arithmetically, basically, you just subtract. Here you have lots of random error and also systematic error as well. You can remove the systematic error, and then you're back to this situation where it's accurate but not precise. So I wanted to talk about standard deviation, because standard deviation, you meet it a lot, and why not start early? Standard deviation is a statistic, is a measure of spread, is a measure of how spread out your data is. Let's do a simple example. Calculate standard deviation. Table. Just looking for some random numbers. Table of random numbers. Okay. Let's take 12 random numbers. I'll try to explain what standard deviation is using these 12 numbers, yes. So, does anyone know what standard deviation is? You know how to calculate it? Okay. Not how to define it. Okay, standard deviation. So, but you all know how to calculate the mean. Mean is simple. Mean is you add all the numbers, so 52 plus 06 plus 50 plus 88. Maybe that's not the best set of numbers to use, 37 plus etc. And then you divide that by 12. Okay, let me do this quickly. 52 plus 37 plus 82 plus... You know what? Let's use an Excel table because Excel. Because why not? Nope, not this one. This will be very useful to you. Promise. I'm not just doing random stuff. So let's call it X. So 52, 37, 82, 6, 63, 57, 50, 28, 68, 88, 02, 28. Okay, so what I want to do is calculate the mean. Well, to calculate the mean, I just need the sum. Sum of these numbers. Here is sum. And the mean, to find the mean, I do equal sum divided by 12. Yeah, it tells you how much values in a data set typically differ from the mean of the data set. That is a very good explanation. So the mean is 46.75. In the next column, I put x minus the mean. X minus the mean. So literally, I do just 52 minus 46.75 minus this value, and you put a dollar sign here. So this is how different is how it's the deviation from the mean. So that we call it deviation from the mean. So literally, it's just the value minus the mean. Okay, does everything make sense so far, please, on a scale of 0 to 10? Now, the standard deviation is the average deviation. Standard deviation. Average deviation. Deviation. The problem is that if you attempt to calculate the mean of these values, look, it says the average is 0. Because some of them are positive, some of them are negative. So finding the average of these numbers is as a pointless exercise. It will always be 0 because of the way it is calculated. So it is pointless to try to find the mean of these. It literally says here the average is 0. What you need to do is you do x minus mean squared. So you square that, and that gives you equal. Take this number squared. Right. Okay. So what I've done is I did the second column, I just squared the numbers. So 9.75 squared is 995, 35 squared is that. And now I calculate the average that equals the sum of these. And then I divide this by 12. This is something that is called the variance. Variance is equal to this. Variance. So variance is the sum of deviations squared. And finally, the standard deviation is the square root of variance. Is equal to the square root of the variance. That's it. That's what a standard deviation is. Okay. So find the values. So the algorithm first, find mean. Second, find x minus mean for each value. 3, find x minus mean squared. 4, find average x minus mean squared. And 5, take the square root of average x minus mean squared. And that's your standard deviation. The standard deviation shows you how much on average the values are differ from the mean. standard deviation. How much on average the values differ from the mean. As a rule of thumb, 70% of values fall within mean plus or minus standard deviation. Sorry, I didn't use the symbol. Standard deviation is sigma, and the mean is mu. We use mu for mean and sigma for standard deviation. Okay. It is. It is the RMS velocity. It is exactly what it is. Yeah. Root mean squared. Yes. So the standard deviation is root mean squared deviation. Root mean squared deviation from the mean. As a rule of thumb, 60%. So for example, if you take the height of males, height of male students, you will have something like an average of 170, and you will have a distribution. This is the probability density. And if you take the standard deviation, like standard deviation is, so the mean is 170 centimeters, and the standard deviation is, well, let's say 8 centimeters. That means approximately 70% of students fall within approx 70% are in the range 170 plus or minus 8 centimeters. I don't know if that's true. That's just this example out of thin air from my head. Good. And now we are back to absolute and relative uncertainty. So we have mentioned that in the very beginning. So absolute uncertainty is the actual uncertainty. So I measure my pen, okay, and it is 138 millimeters. So my pen, 138 millimeters. Now the ruler is accurate to it has a 1 millimeter division, right? However, there is an uncertainty where I put my pen here on this side. There's a 0.5 millimeter uncertainty because I can be wrong by 0.5 millimeter either way. And I have a 0.5 millimeter uncertainty on the other side. So I have in total a 1 millimeter uncertainty. So plus or minus 1 millimeter. So the length of my pen is this. The absolute uncertainty is delta L, which is 1 millimeter. The percentage uncertainty, or the relative or percentage uncertainty, is delta L divided by L, which is 1 millimeter divided by 138 millimeters, which is approximately 1 divided by 138. That is 0.0 0.7% uncertainty. Does this make sense? Do you have a question? And the next is called propagating uncertainties, the next section, which is probably the biggest section of the assignment. Propagating uncertainties. When you multiply propagating uncertainties, when you add values, add or subtract, you add absolute uncertainties. Okay. Example. The length of a rectangle length is 31 plus minus 1 millimeter, and the width of the rectangle is 18 plus or minus 1 millimeter. The perimeter is L plus width. That would be 31 plus 31 plus 18 plus 18. Now plus or minus 4 millimeters. So that would be 31 plus 31 plus 18 plus 18, 98. So that would be 98 plus or minus 4 millimeters. So that's the uncertainty in the perimeter. But when you multiply, so if you were subtracting, you would also add the uncertainties. That's very important. So when you're subtracting values, you still add the uncertainties. And B, if you multiply or divide, you add the percentage uncertainties. Okay. So the length, the uncertainty, the percentage uncertainty in length is the delta L divided by L, which is 1 on 31, which is 1 on 31, which is 3.2%. The uncertainty in width is delta W divided by W, which is 1 over 18, which is 5.5 or 5.6%. So the uncertainty in area, because area is length times width, of course, the uncertainty is the uncertainty in length plus the uncertainty in width, which is 3.2% plus 5.6%, which gives you 8.8%. The uncertainty in area is going to be 8.8%. So we'll calculate the area. Area is length times width, which is 31 times 18. 31 times 18, 558, 58, plus or minus. And now we find 8%, because you know the uncertainty is 8%. So times 0.0088, which is 49 plus minus 49 millimeters squared. The problem is you cannot leave the absolute uncertainty to two significant figures. This is it's like how tall are you? if somebody asks me, how tall are you? And I will say, my height is 178.394 centimeters, you know, plus or minus 2 centimeters. It's like, what? That doesn't make any sense. You wouldn't, like, how can you say your 2 centimeters uncertainty when you're claiming 6 significant figures? That's ridiculous. So if it's like this, then you have to scrap these numbers because they automatically become insignificant. The moment you state your uncertainty, these values become insignificant. The same, you can't say my height is 178 plus or minus 2.149 centimeters. How can your uncertainty be so big and yet you're claiming to know your uncertainty to 4 significant figures? That's not possible. So uncertainty can only be given to 1 sig fig, and the value has to be rounded to the same decimal places. So like that. So your correct value, so incorrect, correct. Let me, you know what? Let's do some more incorrect. 178 plus or minus 2.149. That's incorrect. 178 plus or minus 0.394 plus or minus 2. That's also incorrect. Incorrect. But the correct is 178 plus or minus 2 centimeters. So one significant figure always. This is the same decimal places as uncertainty. All right. So this is the correct way to present a value in physics. The relative uncertainty in percent of a resistance. So this is the equation. You know the voltage to 3% and you know current to 7%. So the percentage uncertainty in V is 3%. Percentage uncertainty in current is 7%. That means the percentage uncertainty in resistance is delta V plus delta I, which is 3% plus 7%, which is 10%. Easy. Very straightforward. The speed of a car. Okay, so notice, yeah, 1 decimal place, 1 significant figure, and 1 decimal place. So that means this is on decimal place as well. 1 decimal place. Okay, same here. 1 significant figure, 1 decimal place, 1 decimal place here. Distance, so that's a distance, and that is a time. So delta S, whatever S, so the uncertainty in distance is 0.1 divided by 20.0. 0.1 divided by 20, so that's 0.5%. 5%. The uncertainty in time is time over time, so it's 0.1 divided by 1.3. 1 divided by 13, which is 7.6, 7.7%. 7%. So that means the uncertainty in the speed, in velocity, is the percentage uncertainty in distance plus the percentage uncertainty in time, which is 0.5% plus 7.7%, which is 8.3%. Now, 8.3% of Well, speed. Speed is 20 divided by 1.3, which is 20 divided by 1.3, which is 15.4, 15.4 meters per second. Of 15.4 meters per second is times 0.083, which is 1.2, well, 1.3 meters per second. And remember, one significant figure only for uncertainty. So that's 1 meter per second. All right, so the answer that the speed is 15. You have to round it. 15 meters per second. Meters per second plus or minus 1 meter per second. So that is important. Okay, this is how you solve a problem like this. Same thing here. The last, I don't have time, so sorry. I don't have time to do this one, but I will do this one. The radius of a circle is 2 plus minus 0.1. So the radius is 2 plus or minus 0.1 centimeters. Find the area of the circle with uncertainty using derivatives. Okay, so derivatives are really clever because what you can do is you can differentiate, and the maths assignment is on differentiation. So we find the area. Area is pi r squared. Now, if we differentiate this with respect to the radius r, dA over dr, we're going to have pi multiplied by 2r, which is 2 pi r. The derivative of area has the same formula as the circumference, and that's not a coincidence. And if you take the volume of a sphere, which is 4/3 pi r cubed, and differentiate it, dv dr, you will get 4 pi r squared, which is the formula for the area of the sphere. The science, we won't publish them today. Sam, I will leave this to you to figure out why. This is a fantastic, this is a really good exercise to figure it out. It's a very important consequence, but I don't have time to do it today, unfortunately. So, what this is not relevant to this question. We found the derivative. Now, the relative uncertainty for area is the uncertainty in area divided by area. But because we're doing derivatives, we replace with dA divided by area. Okay, so let's express dA from this expression. So dA is equal to 2 pi r multiplied by dr, and which will plug it into here. So 2 pi r dr divided by area, which is pi r squared. Pi cancels, r cancels, and we're left with 2 multiplied by dr over r. So the percentage uncertainty of the area is double the percentage uncertainty in the radius, which is 2 delta r. And remember, we multiply radius by radius, so of course we have the uncertainties add up, so that makes it double the uncertainty. And now we have the uncertainty in the uncertainty in radius is delta r divided by r, which is 0.1 divided by 2, which is 5%, that means the uncertainty in area is twice that, delta R, which is 10%. And then we just find the area. So the area is pi R squared, which is 2. So it's 4 pi, which is approximately 4 times pi. 12.6 centimeters squared. And then the uncertainty is 0.1 times 12.6, which is 1.26 centimeters squared. So the area is 12.6 plus or minus 1.26 centimeters squared. We can't leave the answer like this. What do we need to do? What do we need to do here? Round uncertainty to one significant figures. Yes, so it's plus or minus 1 centimeter squared. And then what do we do? Round the area to the same dp, so 13. Yes, and that is your answer. All right. Uncertainty to one significant figure, and then the value to the same dp. Lovely. Okay, we overran a little bit. Thank you for your attention, and I will publish the assignments right away. So right now, and they will be on the assignments section of the of our website. So here you are, and of course the webinars, the webinar schedule is here. So for the assignments will be if you get in, the assignments will be submitted on Canvas. If you don't get in, you can submit the assignments to Google Classroom, right? If you want to do COMPOS follow along, you can do it on Google Classroom, and you will be sent a link. Apologies if you haven't received that yet. So, okay. All right. All right. See you next. Oh, see you on the 22nd, the 5th of November. Right. See you all.